In this lecture, I'll go ahead and show you a little bit about the 1D consolidation, and we're going to break it down into more of these time dependencies. So with our start, as again we've seen before, the Springboks analogy, again the analogy goes that as you add pressure or stress to your soil on top, and then if you have a porous media which acts as basically a valve where water can come out, over time that water leaks out. Now initially there is stress on that soil which is carried by the water, but over time that then gets carried by the soils in terms of effective stress as that water is leaked out. So your total stress, again, here you can see that that total stress is increased and that remains increased over time. That's the change in stress there. Pore water pressure, again, we said initially is as it is, but when that T is equal to 0, when that stress is applied, it shifts over, and then over time that water leaks out and that stress goes back to 0. At T infinity, it's back to its original position. With effective stress, however, we see that at initially with 0, it starts here, and then that soil carries the stress this way. So you guys have seen all that before. Now we're going to go into this graph here. Normally this graph is shown at the end of this lecture, but I wanted to show you that this is really important because this is what we need to understand. So the whole point of the rest of the lecture, we're going to go through this fairly briefly and then do an exercise with you. But this is just to show what we're trying to find out. So we're trying to figure out this graph, the point of this, and hopefully you guys will understand this by the time we're done here. So let's look, starting off just at the Z is Z over H. So H is the total depth of your soil. So if you're looking at a specific soil all the way to the bottom where you would have some sort of impermeable media, it's all the way to the bottom there. We'll talk a little bit more about that where we have 1 versus 2 down there depending on what the drainage conditions are. But that Z, think of Z as basically the depth in your soil, and then H is the total depth of that soil. Now down here we have the consolidation ratio, and so we're going to explain this first off. Again, the point here is just so you guys understand this graph, and we'll come back and look at the curves within that. But we're just trying to get the foundation of the axes here real quick. So let's just look at the consolidation ratio. Consolidation ratio, you can see here we have the equation for this, and just basically said that the initial void ratio versus the final void ratio, and then its current void ratio. Now, the reason we have a current void ratio is that as you add a stress, over time, that void ratio is going to decrease. You can see here, just as we have consolidation, if we put a stress up here on the voids, over time, that water will leak out and there will be less water in there, and so there will be lower amount of voids in there. So we're decreasing the void ratio, and so the consolidation ratio is basically asking how far along that process are we, how much of the voids have we gone to the final condition that we will reach there. So that is the void ratio. Now, so that gives us again the consolidation ratio down here and basically the depth of our soil that we're looking at. And then again here we want to look at how is this curve created. So just notice briefly that as time goes from 0 all the way to 1, so we're basically normalizing our time here. 0 is right at the initial condition, and then T, as T goes to 1 here, 1 would be straight up and down, and this is where basically we have all the water that's exited that will exit and it's returned. All the stress now is on the soil, and so as we look at this, let's just figure out what these curves are. And so there's an equation that we use to basically figure out these curves, and in order to explain that, we're going to go with this Springboks analogy again. But instead of just having one box, we're going to have incremental boxes here. So we have basically, we're going to look at basically how does water escape from the middle here all the way out. In each of these boxes, you can imagine as that soil is compressed with this stress, you'll get water leaking out here. Now water from a box previously will work its way into this first box and then out. And so if we were to break up this soil into an infinite number of boxes, how does that operate? And so you can see here that as this middle box, as it's losing water out both sides, it's leaking out. This will have the highest basically pore water pressure in it here from the if you're leaking out both the top and the bottom. We'll look at other scenarios here, but just think of this as basically how does water exit from each of these boxes into the other ones, and that's how we're going to create our equation for those curves. So we're going to start out here with the general equation. This general equation, if we look from 1, the flow of water out of a differential compressible soil element is dependent upon the hydraulic gradient as well as the permeability of the soil. So this is the left side of our equation. The left side of our equation, we can see here we've got permeability, the density of water, gravity, and these other constants are basically looking, not constants, but these are basically looking at the water flowing out of our soil. So again, we have our pore water pressure and dependent upon Z and T. So that's 1 is the flow of water outside of that cell. Now, we're going to relate this to our second part here. This second part is the flow of the pore water pressure through effective stress. So pore water pressure is directly related to effective stress, and it's based on this equation. This AV, again, if you look at the consolidation graph, as that consolidation adds, if we add more stress to that, you're going to get this constant over a certain range of periods. It's synonymous with basically the elasticity in something like a metal or something like that. So this is basically relating again our using effective stress in the pore water here to the amount of water leaving. So you can think of the amount of water leaving, it's going to affect what that pore water pressure is, and within that basically the effective stress. So if we break that down, what we're going to do is we're going to take out all the constants and we're going to combine that into CV, and you can see here we have the DZ and the DT cancel, and we're left with this here. And so again, if you want to look at what CV is, this is just constants for our specific soil. Again, permeability, density to water, gravity, initial void ratio, and our AV. Again, this is constant over a given small sections of strain. So that is our equation. That gets a few assumptions associated with it. So we want to make sure that this equation has soil homogeneity. Darcy's law holds, fluids and solids are incompressible, 1D flow, so we're just dealing with one dimensions again here. Small strains, so the small strains, that allows AV to be constant as well as permeability, and again, no secondary compression is acting here. So how does time play into this? That equation, basically, if we solve that equation, it will represent one of these lines here. And so how does time come into play with that? This time factor is going to take that CV, this is which we just talked about here. It's also going to take time and our HDR into consideration. And what we want to focus on here is the HDR, that's the length of the longest drainage path. And so in order to illustrate that, if we have a soil, and the important thing to note is here we have porous media on top and bottom. So for this one, the length of the longest drainage path is actually going to start in the middle and act and operate out. So our HDR is actually H over 2. And so that's why the this consolidation graph actually looks like this, is we want to look for, in this case with porous media, we have a scenario where from the middle is the longest path. Now, you could have a scenario where if you have an impermeable media down here, something, some clay layer or something of that nature, in this case here, our HDR is just going to be H, because the longest path is from the bottom here, because no water is leaking out the bottom. It goes all the way up to the top there. So last thing to note here for this brief little lecture is that this graph here, if we look at these, what these represent is basically at a given depth, how much is already consolidated. You can see that at areas that are closer to the surface, or closest from the middle of the drainage path, this has an impermeable surface on top and or a permeable surface on top and bottom, and so furthest away from that, basically those are going to be the portions that are consolidated first, and then this interior part here is consolidated last. Now we can break that down into time, and so over time again you can see that time initially at 0, nothing is consolidated, so we have a 0 consolidated ratio, and that at time 0 is basically all the way up along here. And so slowly over time, again, the top portions consolidate first as that pore water pressure releases instantaneously right on the surface, and as it goes progressively through the soil, The middle part, again, as long as our top and our bottom have a permeable layer, are going to have or in the middle is where our consolidation is basically the slowest, and so the consolidation ratio is the least along this line here. Now, when we're looking at soil, we typically don't look at each portion of the depth here, but what we do is we break this down into average values. And so for basically an average value of consolidation at 0.1 is basically a time representing 0.008. And so what this is saying is that over time, basically you come at a given, let's say this, at a given time, you have an average consolidation. And we're looking at an average consolidation underneath whatever structure it is. We don't want to look at individual points here, but we want to know what the average is, because if we know the average, then we can back out and look at the total settlement, and that's what we'll be talking about next week. So that is the brief portion of our lecture. Again, the whole point is to understand this graphic here. And I think the best way to do that is actually do a little example here where we talk a little bit more about it, and we will do that here in just a second. So go ahead and look at your guys' example, see if you guys can work through that a little bit, and then I will go ahead and work through that here. All right, now that you guys have made a valiant attempt at this problem, I'll go ahead and show you the correct approach here. So here's our soil. Again, you may not be able to tell this exactly, but water is able to flow in both directions here, and so for our soil, it comes out that the water will be consolidated out the top and the bottom. We're asking to plot our UV versus Z after 10 years, and then find the average consolidation, average degree of consolidation. This last part actually we'll leave until Monday when we talk a little bit more about settlement. So I'll go ahead and get started here. We're going to move this up, and basically the first part I have here is basically plotting out different variables. I will have to explain this guy here a little bit more to you, but let's start out by looking at this. If I have given depth here, so again my scenario shows that for 10 meters down in depth, I want to find out now what Z is for each of those. And so Z, as we said, is the equation for that is Z is equal to small z over HDR. And so in our case here, we have Z, but for HDR, the path of drainage that we have in this scenario, this would be 5 here, is the HDR from the middle, since we have drainage in both degrees, this is HDR is equal to 5. So now for each of these, we'll just basically plug in Z to here. So Z at 0, that's obviously going to be 0. At 2.5 over 5, we get 0.5, 1, 1.5, and 2. So this is the reason when we do have drainage in permeable surface on top and bottom in HDR starting from the middle out, we will see that our Z comes to 2, and that's why on this graph here for Z, you can see that that comes from 0 all the way to 2 there. So now, based on that, we want to be able to look and find what our UZ is. Now, if you look at UZ, that's the consolidation ratio. We have the different heights there, but we don't exactly know what time factor we have. So the next step is actually to find this time factor. And so if we come and look at our equation for that, T is equal to CV times T all over HDR squared, which is this is a given, so 5 times 10 to the negative 8th meters per second, or meters squared per second, times time, which is 10 years, divided by HDR, which is 5 squared. And that gives us 0.63. So what that means is that for a specific time that we're looking at, if we look at this graph here, we know that our time factor is 0.63, so we're along this line here. Actually, I'm sorry, a little bit between this line and the 0.70. So all the way along there, that's where our line lies for consolidation after 10 years. So again, as the time goes on, you're basically going to find that you will line up along this graph here. So if I go ahead and pull data off of that, if I just look at the 0 points from top and bottom, we can find that this always converges to 0 on top and bottom. So these are the easy ones. At top and bottom, we have 0 and 0. Now if we look at 0.63 at 1/2, that's one of our variables here, 0.63. Somewhere right down in here, we're going to be I have a 0.81 approximately. 0.81. And then if we find on the graph 0.73 and 0.81, these top and bottom ones should be the same there. I will show you again for 5, 0.73. If we come right through here, it's going to be approximately 0.73 right in there. Okay, now for this next one, this is an equation I actually didn't give you, UE. This is defined as excess pore water pressure. So the equation here is 1 minus UZ times 100. What this means is that as water is expelled in consolidation, there's still an excess amount of water in there. So the question is how much percentage of water is still, or how much water is still left in there in terms of pressure. This is the way we find it through this equation. And I will say that this other one, U naught here, is equal to rho W GZ. So this is basically just our static pore water pressure in there at various depths. So what we will plot this out, you will see that at these different points, 0, 19, you can see that that 19 corresponds, if I take 0.19 off of this value and multiply it by 100, it's going to give me my pressure there. 27, 19, and 0. Now as well for these, which you guys have done before, this again is the rho of water times G times Z. It's going to be 0, 43.5, 49, 73.5, and 98. So what does all that mean? Great question. So what we're going to do is actually going to plot that out, and hopefully that'll bring some resolution to this. And so I'm going to bring this over to the next page. We're going to start out with basically going down like this. This is going to be our static pore water pressure. We'll say U naught. This is again for static. It's just basically coming down at an angle here. The further down you go in the water, it's linear, and that pressure increases with depth. Now, if I put this line here, this is going to be at time is equal to 0, T equals 0, what our pore water pressure would equal. Our pore water pressure is basically 100% here, and so we have 100% of that pressure that all goes into at that water, onto pore water pressure in terms of stress, and again, this is going to come back over time. And so what we will find is after 10 years, we should see something similar to, this is my 10-year mark. And let's see if 10 years there. And what you'll find is this, the UE values that we have, let's look right at the middle, our UE value was 27 here. Again, this proportion is a touch off, I apologize for that. But 27 there, up here we have 19, and down here we have 19 as well. So what this is basically saying, the values that we plotted here, again, these values here, the UE, this is the excess pore water pressure in terms of percentage there. In terms of 100% is all the way out here, and from this U naught here, how much is receded. And we're still at 19% left in these regions, 27% left here, and 19% there. So that is basically looking at the pore water pressure, and that helps us see how this graph here relates to depth in that pore water pressure. Now, we'll just do another brief thing here, and this is the average degree of consolidation. So if we were to look at this and ask, okay, this is the consolidation at each point here. So at a given point, I can find actually the exact amount of consolidation there. But we very rarely look at each individual point underneath a foundation or underneath some sort of soil situation where there's settlement. We will want to know actually over that entire depth what the total average settlement is. And so the average degree of consolidation, then, we are going to find that off of this graph. That graph here, what we said is that T is equal to 0.63, so that comes in somewhere around here. That's going to bring us down into this region here, bring it across. That's about 83%. 83% there. Average degree of consolidation. So from the graph, we see U average is equal to 83%. Now, I will give you a sneak peek, and this U average is equal to ST all over ST, and this top one is equal, T is equal to T, this is T equal to infinity. What this means is basically of the total settlement that we will receive, if I have this settlement, we're basically 83% consolidated, or 83 that settlement has happened, occurred on average there. And so again, the ST at T equals infinity, when that soil comes to a complete full settlement there versus what it is at our time T, this is very much time dependent, and so what that is. And so we're going to look more at this idea of settlement, and we'll actually get into this on Monday. We'll go ahead and give you guys that for now. Please work through this, and we'll see you guys on Monday.